Thank you. It's a pleasure to be here. I appreciate the invitation. I'll tell you about some of the work that we have been doing recently under the general theme of quantum simulations. And I want to begin by acknowledging my collaborators, younger collaborators who did all the real work. So most of my talk will be about cold atoms, and here the main credit goes to Annabelle and Fabian, and also on the ion-based simulator. So here theory was, and sort of collaboration experiments was primarily done by Dries and Kushal. And what made this work particularly rewarding was the opportunity to interact and collaborate with several experimental groups, in particular with a group of Emanuele, Bloch in Munich, Levin van der Sijpen in Delft, Marcus at Harvard, and the group of Chris Monroe and Marcus Ettin in Maryland, but now they moved to Duke. So this is a brief outline of my talk. I'll skip the introduction. Obviously, we're here at a conference on quantum simulators, so I don't need to explain to you why simulations are useful and important. So I'll just sort of try to go over a few examples which I find very interesting. And so the first I'll talk about cold atom simulators and optical lattices, then show that some of the themes are also present in simulators based on quantum dots. And then I'll talk about simulators using ion-based quantum computers, and here the emphasis will be to try and use simulators for things outside of the immediate interest of physicists, but to try and reach out to people interested in other sciences, in this case biomedical research. So, okay, let me start by talking about quantum simulations with ultra-cold atoms. And the general idea is that there's a paradigmatic model called the Fermi Hubbard model, which many people believe represents physics of high TC cuprates. This model basically consists of fermions hopping between neighboring sites and strong on-site repulsion. And fermions and optical lattices provide a fairly faithful representation of this model. And what has been happening in the last few years is that our experimental colleagues developed the technique of quantum gas microscopes. What this means is that they can measure every particle in the system. They take snapshots of many-body states. So what you see here is not a kind of artistic kind of vision of what experiments look like. These are results of an actual experiment. So where you see kind of a red dot, this is when in experiment they measured fermion with spin down. The blue dot corresponds to a fermion with spin up. So you can somehow, at least I sometimes draw analogy between these pictures and the style of painting called pointillism. This was a certain kind of direction in Impressionist painting, where instead of brush strokes, they use individual dots to create the striking images. So a large part of the beginning of my talk will address a question: how can we take this pointillist image of a many-body system and learn something about interesting many-body correlations? So I'll sort of not talk about like physics of the Fermi Hubbard model. Obviously, it's kind of a big field. I'll just, for non-experts, I'll just bring one important fact, that these systems are strongly dominated by sort of tendency of fermions and neighboring sites to align anti-ferromagnetically. You can understand this from basic perturbation theory. Imagine that we have strong site repulsion, therefore we have fermions avoiding double occupancy. However, they can still create a virtual double occupied state, but this is only possible when spins are anti-aligned. And that's why very often effective interaction, kind of non-local interaction in this model, is represented using this Heisenberg anti-ferromagnetic exchange. And what is important to us is that this is perturbation theory, so it goes as square of the tunneling between the sites divided by the energy of the intermediate state, which is repulsive U. Okay, so now if we have just, like one particle per site. We just have this perfect anti-ferromagnetic order, but let's look at something more interesting. Let's introduce one charge carrier, in this case, one hole. And let's consider what happens as this hole moves. It reshuffles spins, and you see that something unpleasant happens. Like, all these spins used to be perfectly anti-ferromagnetically correlated, but the moving hole leaves behind a string of flipped spins. And therefore, this sort of reminds us of a certain string which is left behind the point where the hole started and where it is at any given moment. So by drawing analogy to one-dimensional systems, people call this kind of, you reach this origin as a spin-on, this is a colon, but just by analogy with 1D systems, but in 1D, the spin-ons and colons independent particles, these are solitons. For us, in 2D, they are connected by this kind of string that has a linear tension. And there have been several suggestions going to many years ago that one can think about such propagating hole in an anti-ferromagnetic environment as a bound object of a spin-on and a colon connected by a linear string. And that obviously reminds us of mesons in high-energy physics, where we know that mesons consist of pairs of quarks. Okay, well, can we make something quantitative out of this picture? Well, let's first look at experimental data. So this is data from Bloch's group. What you can see here is 3-point correlation functions. So basically, in this experiment, this doublen, and actually doublen really is equivalent to a hole. There is exact symmetry in the Fermi Hubbard model. It's free to move anywhere in these two planes. However, what we want to understand is spin correlations relative to the doublen, because we saw previously that spin correlations should be messed up in the vicinity of the doublen. And that's what they plot. So like here, as we said, doublen can be anywhere, but for the point, in order to understand this correlation function, like when we represent them, we always put the doublen in the center. And here, this is color coding of spin correlation functions. But they are, you can see they are conditional on being a certain distance away from the doublen. Therefore, one should understand this as really like whole spin-spin correlation, 3-point correlation function, which say is not available in traditional solid-state systems. And you can see that if we just look at nearest neighbor correlations, okay, they're largely away from the doublen. They're just somewhat reduced in the vicinity of a doublen. Okay, that's what we kind of expect, that doublen messes up the spins, but things are not too dramatic. But if we look at the diagonal correlations, we see that things are much more interesting. So away from the doublen, they are ferromagnetic, right? So and that's what we expect. If we look on the diagonal spins, the same sublattice should point in the same direction, but next to the doublen, they actually even change sign. So why does this happen? Well, there is a very simple cartoon how you can understand this. So remember, this is our hole before it started moving in the ferromagnet. Now this hole moves. And these two fermions, which used to be nearest neighbors, now find themselves as next nearest neighbors. Therefore, when we measure this diagonal correlation next to a hole or a doublen, we will have to average correlations which are originally kind of diagonal correlations with the ones which used to be nearest neighbor, and which now, because of the whole motion, become next nearest neighbor. And so as a result of this averaging and the fact that nearest neighbor correlations are stronger originally than diagonal, we see that next to the doublen we end up with anti-ferromagnetic correlations. Okay, and so we have some data that we can try to describe. How do we describe it? First of all, we want to come up with a model that describes kind of this spin reshuffling in the presence of this meson-like object. And the idea is that, okay, so the spin on principle, it can move due to exchange interaction, but as a first approximation, let's even freeze it, because this hole can move with an amplitude t, which is much larger. And then how do we represent this motion? Usually if you just look at single particle quantum mechanics, you represent it by an instantaneous position. But in this case, we need more information, because depending on how the hole propagates, it leaves behind different spins. You can easily convince yourself that the appropriate lattice is a so-called beta lattice, right? Every point on this lattice describes a corresponding trajectory, right? So if I choose a certain point, it just correspond to a certain way how the hole moved, and therefore a very specific string that's left behind. And then what we have to do is just solve a tight binding problem on this beta lattice in the presence of linear potential. And it's something that it's generalization of what you obviously remember from your undergraduate quantum mechanics class. It's like particle in an electric field. Yeah.
Are you allowing loops? Because
this is so-called this is so-called Tragman loops. So if you look at they're important for certain things. For, let's say, this kind of change of spin correlations, their fraction is so tiny that you can safely disregard them. When you want to talk, okay, it's a separate story that if you look at TJZ model, certain objects would not move without the loops. So usually it's enough to put it by perturbation theory at the end, just because their weight is extremely small compared to other strings. Yeah.
Sorry, so can you think of these 3-point correlations as quasi-particles that move around?
No, so this, okay, so this, like, real quasi-particle is a magnetic polaron that has an internal structure.
Yes.
So this, like, charge spin, that's just the way, you know, it's just a way we measure correlation function. It doesn't.
Okay, so it's not an object.
So what is an object is this magnetic polaron, is this spin on colon plus a string.
All right.
Thank you. Other questions? Right. Okay, so now that I said we can sort of solve this tight binding model. This gives us a wave function of the string. This gives us knowledge how, let's say, motion of this colon will reshuffle the spins, and then we can compare theory to experimental. So you can see we get a fairly good agreement. So this, again, like what is plotted here is, as we said, like this charge spin-spin correlation. So as a function of the distance to the doublet, we measure nearest neighbor spin correlation, and that's what we discussed before. The larger away from the doublet gets smaller closer to the doublet, which is what the geometrical string model gives. Or these diagonal correlations, again, as a function of the doublet, you see they even change sign to a certain distance. Okay, but then what our experimental friends became more ambitious, so this is now, we'll describe experiments from Marcus Greiner's group led by Christy Chu and Annabelle Bort on the theory side. And as we said, that as a whole propagates, it leaves behind this kind of string of flip spins. So the question is, can we see them in the data? So this is how they did it. So this is, okay, an image, like original image, but I sort of need to explain that in experiments of Marcus and his group, at that point they didn't have the ability to image at the same time spin up and spin down. They had lower temperature than Emanuele's group, but they had to decide whether they image spin up or spin down. As you'll see, it's not a showstopper. So let's say they decided to measure spin up, the blue particles. So then the other spins will appear as empty sites, doublets as well. Okay, so they image just the spin up sites. They compare this to the perfect checkerboard, which would be a classical antiferromagnet, and they look at the difference between this perfect checkerboard and what they measure. Okay, so these are the 4 sites that are different connected to each other. Here there is a pair of sites which are different from each other, so let's just call them strings. And we sort of mark them in every image. And then we say that this image has one string of length 4, 2 strings of length 2, and 1 string of length 1. And then they plot distribution of these strings as a function of length. And what one should realize is, obviously, even at half filling, we're not dealing with a classical antiferromagnet. There are fluctuations. Therefore, these points below, they correspond to the spin distribution just due to thermal and quantum fluctuations when antiferromagnet. Then these points above, well, they show the increase in the number of strings when the system was half doped. And it looks like, oh, it's a slight change, but it's a logarithmic scale. So you see for longer strings, the probability to have longer strings goes up by almost a factor of 10. And you can check, or maybe we have longer strings just because we removed some of the sites by, because after all, we're doping. No, just randomly removing sites would only shift the distribution of strings to this yellow line. You can see it would be insufficient. So the real increase in the number of strings comes from the whole motion. Okay, so this was individual polarions. Of course, we want to understand many-body properties. So, okay, I'll just describe again one of the experiments. So in cuprates, depending on the phase diagram, there's an interesting transition that if we sort of close to antiferromagnetic state, the system looks very unusual. It's kind of opposite of what we expect from a usual Fermi liquid. Say with lowering the temperature, we have quasi-particles which are defined worse than at high temperature, whereas when we go to overdope, it actually we recover conventional Fermi liquid-like behavior, and this crossover from sort of non-Fermi liquid to Fermi liquids appears to not depend on temperature. It just happens at a certain filling factor. So the group of Emanuele analyzed data on the quantum gas microscope, and I'll just show you some of the results and try to argue that we see the same crossover in their data. Again, so the simplest correlation function that they looked at was just 2-point correlation function, right? So, and they chose the ones which in an antiferromagnet, in a Mott insulator look ferromagnetic. So in this case, it's diagonal. So this horizontal axis is doping. You can see here for undoped system, they look ferromagnetic, but then as doping is increased, actually they change sign and become antiferromagnetic. Then here, this is again next nearest neighbor now in horizontal. Again, it's ferromagnetic in the Mott insulator, but then as the system is doped, it becomes antiferromagnetic. And this goes on even for longer range correlation functions. And the idea is that in the Fermi liquid, we expect correlations to be antiferromagnetic. It's just Pauli principle that we're much more likely to find fermions with opposite spin next to each other than with the parallel spins, because spins with the parallel spins have some kind of repulsion, some effective repulsion due to Pauli principle. One can also convert this 2-point correlation function in real space to momentum correlation functions, how we usually see them in neutron scattering. Then from a doped Mott insulator, we see a peak at pi, that's our antiferromagnet. And only beyond the filling of around 30%, they split into what we would expect for weakly interacting fermions we see in commensurate structure. So the more data, but more or less they all sort of converge to the same picture, that to the left of, let's say, 30% doping for the Hubbard model, we see a system that can be described as a liquid of polarions that I presented to you earlier, whereas for larger doping, we go to more traditional Fermi liquid-like description of the system.
What is the temperature?
So in these experiments, it's probably around like 0.6 J. So it's not very low temperature, but as you can see, this crossover from non-Fermi liquid to Fermi liquid occurs at fairly high temperature. The questions? Okay, of course, the big question that people have is, do we see pairing? And so I want to tell you about the first observation of magnetically mediated pairing, again in the group of Emanuele. And here the trick that was suggested by Nadav and Fabian was to use something which is kind of an interesting tool, which is not, it's kind of not easy to realize in traditional solid-state systems. And the idea is as follows. So let's start with a ladder. And then, okay, if you can, we can now ask, okay, do we have pairing? Let's say if we dope it, do we find holes sort of sitting on the same run? So on one hand, it's clearly beneficial because this way, let's say we can have kind of nice arrangements of singlets across the ladder, but on the other hand, like in this arrangement, holes cannot tunnel individually, right? Whereas if they are away from each other, well, they can lower the energy by having independent tunneling. So, like naively, at least, it's a competition between some kind of magnetic binding, which is superexchange, and tunneling, but tunneling is expected to be larger. And so, what was realized by Nadav and Fabian was that what one can do is actually apply a bias potential, sort of have a different, if you wish, energy for the, let's say, upper chain versus the bottom chain. And this achieves two results. If this bias is particularly strong, then actually holes cannot tunnel. Single particle tunneling is suppressed. However, now if, let's say, this sort of red fermion goes to the neighboring site, the double occupied state has an energy not of U, but U minus delta, U minus bias, and therefore we enhance exchange interaction. Therefore, applying this bias actually gives us two things which are both beneficial to pairing. It suppresses single particle tunneling and it enhances exchange interactions. And so when this idea was implemented in experiments, immediately it was sort of these pairs became visible. So this is shown in this plot. So this is correlation function of two holes as a function of distance between them. And you can see that without the bias, right, so actually we're less likely to find two holes on the same run than when they're further away from each other, just because of the cost of tunneling. However, when there is a bias, and in this case it's fairly large bias, then we actually have an obvious increase in the probability of finding two holes on the same run.
Sorry, question. So you have in this figure the grid like four times, I don't know, 8. But then within each point, there is additional grid. Like there is meaning to these points?
No. Like basically, you just look at it like, just finite resolution. Either particle is in here or not. Yeah, that's all. Other questions?
How do you distinguish from pairing and just charge density wave?
That is a good question. On such a small system, it's hard to tell. It's only like 8 sites long. So I don't know if I have, sorry, I did not put the slide. So what you can clearly see is when they put more than 2 holes, they try to stay away from each other, right? But whether it means that we're dealing with, well, strictly speaking, 1D, it's always a Latinger liquid, right? We can only talk about like Latinger parameter. So experimentally, I mean, obviously from the MRG, we can tell you what it is, but experimentally at this point, yeah, we cannot tell. We can just say that we have pairs, like there is actual binding between them. They stay away from, they have fairly strong repulsive interaction, whether they will form charge density wave or kind of more superfluid type Latinger liquid, we cannot tell yet. Good. Okay, so now I'll just maybe say a few more words that this kind of domain of exploring Fermi Hubbard model is not just done with cold atoms. There's also interesting developments on the side of quantum dots. So in particular, there has been a long-standing sort of conjecture of Nagaoka ferromagnetism, and it's kind of an interesting statement that I give you a very kind of baby version of this statement. Consider 4 sites, right? And then we put 3 fermions on these 4 sites, and then we ask what's the lowest energy configuration on these sites? Is it when all the spins are pointing the same way, or spins sort of trying to be as antiparallel as they can be? And based on what I told you earlier, you would be able to say, oh, but we know that we want to have anti-ferromagnetic interactions. Therefore, this should be low energy. Well, actually, there is another argument for why ferromagnetic interaction is dominant, and this is if we have ferromagnetic orientation, then if a hole moves this way or the hole moves on the other trajectory, these 2 trajectories will interfere constructively, and therefore motion of a hole in the ferromagnetic environment is actually energetically kind of lower, so it's beneficial. It lowers the kinetic energy of a hole. And that's why for, let's say, this placket, one can really predict the transition from orientation when the system will be, let's say, when tunneling dominates, when our primary goal is to minimize the kinetic energy of a hole, we will be in the ferromagnetic state. And so this question was investigated by Living under Siphon group in Delft, and they indeed saw this transition. It's kind of remarkable. Okay, I'll be happy to talk offline, that if you look at the numbers, in fact, energy scales are such that one really needs to include many levels inside individual dots. That naive Fermi Hubbard model should not apply. However, when the dust settles, one also finds this transition between ferromagnetic and antiferromagnetic state, and they saw this in experiments before it was seen in cold atoms experiments. Okay, but now let me move on. So far we talked about using simulators for like problems which are obviously exciting to physicists, but perhaps not to the outside world. So let's try to discuss if we can sort of reach out. And here I want to sort of, to some extent, motivated by the comment made by John Freskel, who pointed out that we have, who suggested that while we can debate whether quantum technology is useful to solve classical optimization problems, that they're very likely to have an input on problems which are intrinsically quantum. And probably many of you know this kind of quantum bullshit Twitter, so this was ranked as a non-bullshit comment. Anyway, so the specific problem that we actually, well, it's more like our colleagues and friends from medical school approached us and said, well, can you guys do something useful? In particular, they have this problem of NMR inference. More or less, you can formulate it as follows. So they take an NMR spectrum of some body fluid, and they want to find out what's the chemicals that gives rise to this. So in particular, like at least as an intermediate problem, they want to understand what's the Hamiltonian that gives rise to the spectrum. So, and in like again some simple cases, small molecules in liquids, we know the rules for constructing the Hamiltonian, like spin symmetric interactions, magnetic field. And what is unusual is that this spectrum really corresponds to the correlation function that's computed at infinite temperature. So the so you can imagine that if you wanted to do, to sort of recover the Hamiltonian, that what you would have to do, you would make a guess about the Hamiltonian, compute the spectrum, compare it to what has been measured, adjust it, then compute again. And if you compute the spectrum sort of most directly, okay, you need, because you're at infinite temperature, all the states are involved, you have to do, essentially diagonalize the entire system, so diagonalize exponentially large matrix. And in fact, you have to do it many times because every time you adjust the Hamiltonian, you have to recompute the spectrum again, and that's why it's a laborious task. So, okay, to cut long story short, so G's cells came up with the idea how, like to compute the spectrum given the Hamiltonian using a quantum circuit, and instead of like for an arbitrary Hamiltonian of this form, instead of exponentially large problem, it actually scales only as n squared. So I'll not, since time is short, I'll not go through the details. I'll be happy to discuss them afterwards. Then, of course, okay, so if you compute the spectrum, you still also have to show that you can converge to the right Hamiltonian. So here Jesus' insight was that if we think about spectral functions, they look very much like probability distribution in like statistics. In probability theory, they normalize, they're positive definite, and so one can apply sort of variational bias approach where basically every new measurement sort of clarifies our guess about the distribution of parameters. Where these parameters really are sort of what interaction strength in the Hamiltonians or sort of effective Zeeman interaction. And you can also ask, okay, well, but how bad is the landscape? And in fact, it turns out that if you start with a completely random guess about the nature of the Hamiltonian, you will never make it to the true value of the Hamiltonian because there are so local minima. Basically, it's the fact that there are so many sharp peaks, you just fit one and then you're stuck. But so far, we found that nature was kind. If you look at molecules which are really relevant, they kind of, if you look at the spectra, they make clusters. And then these clusters actually reflect chemical composition. Say, spectra like this, which have a lot of degeneracies, they come from molecules that have a methyl group, so we have identical hydrogens, or spectra that look the most like chains that physicists are used to. They all, and this is an example of phosphine molecules. So all of these molecules, they have this benzene ring.
This clustering actually works for the favor of the classical method, right?
Sorry, say it again?
The clustering
actually
works for the favor of the classical methods. It's going to be hard to beat it because the clusters are quite small.
So let's talk about this separately, but in this case, you have to start, like when you give a new spectrum, you have to start from the right cluster, otherwise you will not converge. So the idea is that it's, as I said, there are so false minima that you have to be in the vicinity of the right minimum to converge. That's why we have to do clustering before we can do optimization. Okay, so then this is implementation and done by our friends at Maryland, and there were many technical problems. Obviously, you all know that there is a limit on how many gates you can apply, and so we had to work with them to sort of synthesize circuits to in order to make it practical within the limit that they gave us. Also, if you think about the spectra, it has very sharp peaks, so naively you would guess that if you look at sort of time evolution, you do this sort of correlation function by evolving in time, you would have to have very sort of many time points, sort of like 4,000 values of time, and they basically told us, well, look, you have to stop at 100 because that will already take several days. So here, and it turns out Kushal and Dries came up with ideas of compressed sensing which can make it work. But the bottom line is, so here you can see comparisons of, so this is a spectrum of this etc. trial, and it's in zero field, which is usually hard for classical inference. And so this is comparison of the actually measured spectrum to the quantum simulation. So interesting features such as, like, the actual molecule has certain symmetry. As a result, it does not have a peak at j/2, even though there are states which differ by j/2, but there are selection rules which make sure that that peak vanishes. So, and here they implemented the Hamiltonian, which has the same symmetry, but obviously noise does not have the symmetry. As a result, you see an extra peak.
Can you comment how the synthesis, how scalable it was in a way that when you done the synthesis, did you use the fact that you know how to solve the Hamiltonian? So you, that's correct. In this case, you use some knowledge, but in real molecules, you kind of know that it consists of, usually it's several clusters. So all you have to know is, like, you would do the synthesis, helping sort of simplifying work with the clusters which are more weakly coupled to each other. So yes, some knowledge kind of is required. Yes, that's correct. But, you know, in the limit, when they will be able to do, you know, 400 2-qubit gates, we will not need to do synthesis. Fortunately, we had a budget of how many gates they can apply. But, yeah.
Can you have isospectral Hamiltonians? I mean, can you have a situation in which the spectrum is the same, but the structure of the molecule is different?
No, not really. You see, the problem is over-defined. It's like, so your question is, it's like, can you hear the shape of the drum? In classical physics, people asked from the spectrum, can you uniquely reconstruct the problem? So in this case, see, the difference is in the linear problem, there are just a few harmonics and then you add them all up. Whereas in a quantum problem, the number of parameters interaction is like n squared. Whereas the number of energy levels is exponentially in n. So the problem is actually over-defined. That's why there is a unique solution. Yeah?
So you commented that it's important to know how many clusters you have? And
not how many.
Which cluster is starting at?
Yes,
so
that's correct.
The question is, you showed that for 4 spins, we have 4 clusters. How does that scale?
You see, I have a small group. So far, we just stopped at 4. We did not even analyze larger molecules, which of course would be interesting. Yes.
Just a comment. It becomes exponentially large starting with 7 spins. Okay? We have tried that. One simulation takes a month for one configuration.
But you're talking about arbitrary Hamiltonians.
I'm talking about...
No, arbitrary spin Hamiltonians. But you see, I talk about, if we were to do it even with arbitrary 4-spin Hamiltonian, I'm not sure there would be clustering. See, we talk about actual molecules, and molecules have very fixed chemical structures.
Yes, so...
and that's why they come in very specific shape, like a methyl group or a benzene ring.
So
let's talk about this. Let's talk about, in the real world, I doubt it. Okay, so now let's talk about, okay, so so knowing the quality of our simulations, let's say, when can we expect this procedure to be useful? So specifically, what we wanted to ask is, what are the requirements on quantum hardware to be able to do inference for molecules which are actually hard for classical tools? And again, roughly the idea is as follows. Okay, because we implement spin evolution using tractorization. And factorization, of course, requires making smaller steps, delta t. On the other hand, there is a quantum hardware problem, and the more steps you make, then the larger is the error, and therefore you have to balance. So particularly you can compute for a given infidelity of the gates, you can compute sort of what's the resolution of the spectrum that you can get, and then you can ask it what is the intrinsic width of the NMR spectrum, because unlike classical optimization, the advantage of this problem is NMR spectra have their intrinsic width, so we don't have to have infinite accuracy of the spectra, we just have to be as good as nature. It doesn't make sense to be better than intrinsic width. And so what we find is that more or less you can see that if infidelity is at the level of 10 to minus 4, and we can have number of circuits of 100,000, then we can sort of be competitive with the best classical algorithm. And I want to emphasize, so this number, yes, appears in other contexts, but at this infidelity, we do not need error correction. At this point, just kind of quantum hardware this will already be useful to compete with classical algorithms. Okay, so the chair is up. So this, I told you about kind of few directions that we pursued with quantum simulations, Fermi Hubbard type model and cold atoms, quantum dots, and also NMR, quantum assisted NMR inference. Thank you.